So in this lesson, we're going to talk about a specific function called the square root function. And from it, we will learn how to do other roots. So here is our standard we're looking at. And by the end of this lesson, you should be able to at least describe the key characteristics of a square root function and graph them. So let's look at the basic parent function of the square root function. So it looks like this, and I think it says on your paper there at the bottom. And please note that even though we're talking right now about the square root function, we could just as easily be talking about any function that contains a radical. Square root functions, square roots, cube roots, or the inverse of square roots, cube roots, or the inverse of cubic functions. And of course, you can have fourth roots and fifth roots. So these all are just called radical functions when we class them together. So let's go ahead and look at that parent function's points. So if I go ahead and I take the square root of 9, I get a 3. If I take the square root of 4, I get 2. Square root of 1 is 1. Square root of 0 is 0. If I try to do the square root of 2, it's not that I can't do the square root of 2, but I would need to use a calculator to come up with an estimate if I'm not too sure. I know it's pretty close to 1. So that's why I didn't use it as an input, but I could. But if I try to take the square root of -1, square root of -1 is I, but this coordinate plane uses only real numbers, and I is an imaginary number. And that's why, one of the reasons, we have to think about what kinds of numbers we use in the square root function. Anything that's going to make the input evaluate to something that's negative is going to give us an imaginary number. Therefore, we have to restrict it from our domain. So now let's go ahead and graph those and look at our function. So we know we had an input of 0, and we got 0, 1, 1, and 4, 2, and then we had 9, 3. So it starts here, and then it's increasing at different rates of change as we go from point to point. But it looks like that. Kind of looks like a half parabola, huh? Okay, so let's talk about our domain. So where did we start? The first x value we could use was 0, inclusive. And then it could go do anything to infinity. Range was the same. X-intercept was at 0, 0. Y-intercept at 0, 0. Vertex was also at 0, 0. Does it have an increasing interval? By golly, it does. It starts here and it goes up and up and up and up and up. And it keeps doing that until infinity. But remember, we put a parentheses there because it's not increasing at 0. Does it have a decreasing interval, though? It does not, because there's no place where the y values are getting smaller as we go left to right. There also is no relative minimum or relative maximum, and that's because in order for us to have this point right here to be a minimum, there has to be a point on the left side over here that's higher than it. That's why it's not a relative minimum. Here, we talk about the restrictions on the domain. Was there some numbers I couldn't use in my domain? I could not use any number that made this negative because the square root of a negative number is always going to be imaginary. Therefore, I have to say that my x values had to start at 0 and then get bigger because I can only do 0 is the least value I can put as an input in this function. And no asymptotes. So if the radical is a square root, the function is called the square root function. Okay, compared to other functions that we've talked about, basically what it is, it looks like half of a parabola. And it's opening which way, though? It's not happy, it's not sad, it's open to the right. Okay, now let's talk about this one, square root of the opposite of x. So let's go ahead and look at functions. So now this time if I go ahead and I say, okay, what's the square root of the opposite of 9? I would get 3i, which is not real. So instead of using these as inputs, I have to use their opposites because the opposite of -9 is 9, and I can take the square root of that. It would give me 3. And I'm sorry, I can take the square root of that and get a real number. So The square root of the opposite of negative 4 is the same as the square root of 4, which is 2. Square root of the opposite of negative 1 is 1, which is 1. And the square root of the opposite of 0, well, that's just 0. Okay, so not worrying about that. Okay, so here we're going to be talking about, sorry, how to use this for something else. Compared to the parent function, what is this going to look like is what we're going to write there. So I had an input of 0, not 0. Input of negative 1, I got positive 1. Input of negative 4, I got 2. And an input of negative 9, I got 3. So now what's it doing? It's just opening the other way. The parent function was that, but now this one's going the opposite way. So it's what we call a horizontal reflection. It flipped from left to right of its parent function. Okay, so what is its domain? The domain is the opposite of what we had before. Its numbers less than 0 because it's starting from negative infinity and it's stopping here at 0. The range, however, starts at 0 and it goes to positive infinity. The x-intercept still at 0, 0. Y-intercept the same. Vertex, and remember, when I mean vertex, I mean quote-unquote the vertex. It's really like an endpoint. Is it ever increasing? Well, remember we read a line from left to right, and so as I'm going from left to right, I see those points are decreasing in value. So from negative infinity until we get to 0, it's going to be decreasing. No relative minimums or maximums because remember, this point cannot be a minimum because there's nothing to the right of it that is greater than it. And of course, we do have restrictions on the domain. This time, we need all our values to be less than or equal to 0. And there are no asymptotes in these functions. Okay, let's look at some other transformations now. So I already have the graph of the parent function listed. And this time it says y equals 4 times the square root of x. So if I put in a 0, I get the square root of 0, which is 0. 4 times 0 is 0. If I put in a 1, I get the 4 times the square root of 1, which is 4. And if I put in the square root of 2, I get 4 square root of 2, which without a calculator, I'm not sure exactly what it is. And if I put in a 3, I get 4 square root of 3, which again, without a calculator, I'm not sure exactly what it is. And if I put in a 4, I get 4 times the square root of 4. Square root of 4 is 2, gives me 8. So I have 3 points, and I know for sure where there are. By putting in perfect squares, I'm going to be able to, by putting in values that are going to give me a perfect square when I evaluate them, I can go ahead and find those without the use of a calculator. So I have 0, 0. I put in a 1. I got a 4. I put in a 2, and I got 4 square root of 2. 3, 4 square root of 3. But 4, I got 8. So here is 4, 4, 5, 6, 7, 8. So what did it do? So remember that a value outside of the square root function gives us what we call a vertical stretch. And what that means is when we look at corresponding points with the same inputs, this point here had a vertical distance of 4, but this point had a vertical distance of 1. This point has a vertical distance of 8 versus this one is 2. 1 times 4 makes 4. 2 times 4 makes 8. So I'm stretching the vertical distance. So compared to the parent function, it's a vertical stretch. And that happens when the absolute value of a is greater than 1. Okay, so when a is greater than 1, the graph is going to be a vertical stretch of the parent function. All of the points are going to be a times y compared to the parent function. So how does that work? Well, if you remember the key points in the parent function, 0, 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. I'm going to take these y values. I'm going to do 4 times y. That gives me 4 times 0, which is 0. 4 times 1, which is 4. 4 times 2, which is 8. So for those same inputs, I'm getting these values for my outputs. So if I were to happen to transform what I got from the parent function for the 0.93, if I go ahead and I do 4 times 3, I would have gotten 12, which is going to be a little bit off of my graph, which is why I chose not to do it. Okay, and remember those key characteristics. Can you describe the domain, range, x-intercepts, etc.? So on this one, I see that the domain is the same as the parent function, 0 to infinity. The range also. Vertex is in exactly the same place as, so my y-intercept and x-intercepts remain at 0, 0. The increasing interval is from 0 to infinity, same as the parent function. No decreasing, no minimum, no maximum. Restrictions on the domain, same as the parent function. We need our input to be greater than or equal to 0, so we end up with a square root of a positive number. Okay, now this one's going to be a little bit different. We're still looking at what happens when we do a vertical transformation, but what happens when the a value has an absolute value less than 1. Okay, so thinking about how we did it before. Okay, so this is our parent function. It's the big mama. So in our parent function, we use 0, 1, 4, and 9 as our inputs. And so according to what we just did, we said that if the parent function has these outputs for those inputs, we need to take them and we need to do exactly what A says to do. Negative 0.5 times the y. So if I take half of 0, I get 0, and the opposite of 0 is 0. If I go ahead and I do half of 1, I get 1/2, and the opposite of that would be negative 1/2. Half of 2 is 1, and the opposite of that would be negative 1. Half of 3 is 1.5, and the opposite of that would be negative 1.5. So now let's go and graph those. So I have 0, 0, then I have negative 1/2 for an input of 1, negative 1 for my input of 4, and when my input was 9, I got negative 1.5. So what's different? Well, this time it's flipped vertically. And look at our vertical distance for corresponding points. So when our inputs were 1, this point here is 1/2 a unit away versus 1. So this is called a vertical compression. So this happens when the absolute value of A is between 0 and 1. Okay, you go ahead and describe the key characteristics and see how you did. Okay, here's what you should have gotten. You should have gotten that the domain was 0 to infinity, but the range is going from negative infinity to 0. And that's because it's below that y value of 0. Same intercepts and vertex / endpoint, whatever you want to call it. This time it's decreasing. So it's starting to decrease at 0 until it gets to infinity. No relative minimums, no relative maximums. And any restrictions on the domain? Well, this time we can't take the square root of anything that's going to make, that what's under the radical always has to be greater than or equal to 0. So restriction on the domain was x must be greater than or equal to 0, and no asymptotes. Okay, so 2 more. This time we're looking at other types of transformations. This one says square root of x plus 3 and the square root of x plus negative 3. So remember, when you're doing these, always think about your parent functions. So I'm going to go ahead and right here in the middle, I'm going to put x, y, and I'm going to put t for transformation. So in my parent function, 0, 1, 4, 9, I use those as inputs. I got 0, 0, 1, 2, and 3. So I'm going to do this one first, and I'm going to do x plus 3. So what this one is saying is it's saying every point after I do the square root, I'm going to add 3. So this is what it's saying is to take my y, transformation is going to be my y plus 3. 3, 4, 5, 6. And now let's go ahead and graph those. So I have 0, 3, 1, 4, and 4, 5, and 9, 6. So it looks exactly the same, it's just been shifted up vertically 3 units. So if I'm doing this over here, let's see what happens. Okay, so this one right here says square root of x minus 5. So if I start with my parent function, and if that method is a little bit confusing for you, think about what we did before with absolute value functions. We said, okay, when the adding or subtracting outside of the parent function, this would move it, up 3, and this would move it down 3. So what would this one do? It would move it right 5, and this one would move it left 2. So you can go ahead and you can do a table of values, or you can remember what is the parent function, draw it, and then use your transformations. Right 3, 1, 2, 3, and move those functions. What are you actually doing? We're adding 5. Oh, darn it. So what is this one doing? Moving it right 5, and this one, remember, moves it left 2. So what we can actually do is just go back to our function and move all the points to the right 5. 1, 2, 3, 4, 5. And then this one, which was at 1, 1, we would move it to the right 5. And the one that was at 4, 2, we would move it right 5. So now it's at 9, 2. Okay. The reason we had to do that is because if I pick any number below 5, I get an imaginary number. So that's why it's over there. Okay, and if I went ahead and I did this one, everything would be to the left too. So 0, 0, negative 2, 0, 1, 1 would be negative 1, 1, 4, 2 would be at 2, 2, and no stretches, no compressions. Okay, so let's look at putting it all together. So when I'm looking at this, I see that the 2 right there is going to give me a vertical stretch. The plus 3 is going to move it left 3. And this minus 4 is going to bring it down 4. So if I was asked to describe what's going to happen, I would say, I'm going to just abbreviate vertical stretch by 2 times 2. I'm going to move it to the left 3. I'm going to move it down 4. Okay, so parent function, I use 0, 1, 2, 0, 1, 4, and 9. So what are the things that affect the domain? Remember, domain goes with left, right, and reflections that are across the y-axis, or horizontal reflections. So if I take all those points and I move them left 3, that means I'm going to have to subtract 3. So kind of do the opposite of what I thought. Negative 3, negative 2, 1, and 6. What are the things that affect my range? Well, the vertical stretch times 2, and then the down 4. So in my parent function, when I had an input of 0, I had 0, 1, 1, 4, 2, and 9, 3. Those were my outputs. Order of operations, do I multiply or subtract first? I multiply. So I'm going to take each of those and I'm going to multiply by 2, double, and then I'm going to subtract 4. 2 times 0 minus 4. Then we go ahead and do that to the 1. 2 times 1 minus 4. 2 times 2 minus 4. 2 times 3 minus 4. And these make up the points in my transformation. -3, -4. -2, -2. 1, 0. And 6, 2. Okay. Summary of transformations. Okay, so these are the types of transformations that we have: vertical shrink, / compression, vertical stretch, reflection, translations. A translation moves the figure up, down, left, and right. Okay, so algebraically, when we're doing a horizontal translation, we add the h value to each x. And if it's a vertical translation, we add the k value to the y. Okay, so a stretch moves every point on a figure a times from the x-axis, with the points on the x-axis remaining fixed. A vertical shrink moves it also a times the x. Remember, this happens when the absolute value of a is less than 1. That's because you're always going to be multiplying by a number less than 1, which makes it smaller. Okay, shortcut algebraically is to multiply the y coordinate by that positive number for the stretch. And reflection, or shrinks. Reflections, remember, a reflection flips the point over the straight line. Vertical reflections look like this. The negative is outside the square root, whereas when it's inside the square root, it's a horizontal reflection. So vertical reflections, we multiply the y coordinates by -1 or -a, depending on what it is. And horizontal reflections, we multiply all the x coordinates by -1.